Hello. Yeah. Good evening. Yeah. So maybe we can start now. Both coordinators of the colloquium are not available. I can just introduce the speaker and then I'll hand over to him. Yeah. Let me introduce the speaker, Professor Paolo Lipari. He is visiting TIFR, an adjunct faculty member in the Department of High Energy Physics. So this is his second visit. After assuming this position, he earlier visited in November, December 2023. He will be delivering a series of lectures on astroparticle physics at TIFR Mumbai. After that, he will move to UT. There, he will deliver a set of lectures in astroparticle physics school, which is scheduled to take place in the second week of March. Professor Lipari, he is a highly accomplished researcher in the field of cosmic rays, and he is very well known to the community. He does not need any introduction to the community. However, it's a pleasure and honor to introduce him to this audience. Professor Lipari, he embarked on his research journey as a high energy phenomenologist, earning his PhD degree from University of Rome in 1980 with his thesis titled Possible Experimental Studies in an Electron-Positron Colliding Beam Machine using a Hadron Calorimeter in the direction of Proton Beam. In 1986, Professor Lipari transited to the field of cosmic rays, joining the macro experiment at the underground Gran Sasso laboratory. In 1988, he obtained a permanent researcher position in the section of Roma 1 of INFN, and he became research director in 2000. Throughout his distinguished career, Professor Lipari has authored over 350 research papers spanning areas such as high energy physics, gamma ray astronomy, cosmic rays, neutrino physics, dark matter searches, and multi-messenger phenomena. His remarkable achievements in the field were recognized during the 37th International Cosmic Ray Conference, ICRC, which was held in Berlin, where Professor Lipari was honored with the Okile Medal. Professor Lipari is a passionate teacher committed to spreading teaching and research in physics, especially in the developing countries, which has led him to spend months in several countries like Latin America, including Bolivia, Argentina, and Brazil. On a personal note, Professor Lipari, yesterday, while we were chatting, he shared a very fascinating story. In 1976, at the age of 19, he made a solo journey for 4 months across India, traveling from Delhi to Kanyakumari, Bihar, West Bengal, and Odisha. He humorously remarked that it was a dangerous thing to do that time. Without taking much time, I would like to invite Dr. Lipari to give the talk.
So, I think I can use. Can you hear me?
You can use.
Well, for me, it's really a great pleasure to be here in India and to here in Mumbai. Actually, it was not dangerous to be in India in 1976 at all. It was a wonderful time. It was dangerous because I was studying physics, and I stopped my studies to travel the world, and this is dangerous. It's dangerous because you have the desire to do research, to learn, and then you have the desire to visit the world, and so actually you have to adjust these different things. And India for me is a very, very dear place, and it's wonderful to be here. I'm grateful to be able to discuss. So I really have to apologize a little bit. We decided with Professor Mohanty, I will not so much report my own research, but I've decided to make a presentation, a very general presentation, which will be a very quick, very rapid, probably too fast landscape presentation of this field, which I think is really extraordinarily exciting. and in this field of what called multi-messenger astronomy. So probably you heard this introduction several times, but I really think it's important. I mean, the history, essentially until very recently, everything we knew of the universe was obtained by light, by seeing photons. Actually, if you think the word observe the universe, observe means, looking with your eyes. And the history of astronomy has been marked by the expansion of this observing, from optical, what you see, to infrared, radio, X-ray, gamma rays. And if you look at this, each step in enlarging the waveband carried each new window, revealed new surprises, new object in the universe. And what we are witnessing today is a remarkable enlargement of this window, because we don't only have photons of very different properties, of course, but you have really new particles, because you have neutrinos, gamma rays, if you want, are part of this photon band, and cosmic rays. In all of this talk, for me, cosmic rays are relativistic charged particles, protons, nuclei, electrons, and so on. And of course, there is a very exciting development, which is the use of gravitational waves. And these four messengers actually together reveal really a new piece of the universe. I like this expression. You see, cosmic ray, gamma ray, and neutrino, the individual particles carry very high energy. And in fact, actually, this was, and so then they reveal astrophysical sources and astrophysical environment, which are in some sense unique. And I call the high energy universe the ensemble of all these astrophysical objects, sources, environment, events that generate, store very high energy particles. And this is a place full of remarkable objects. And here I'm listing something, and actually I will go very quickly through this. There are gravitational collapses, supernova explosions, black holes and accretion around black holes, gamma ray bursts, and so on. And there are phenomena which are dynamic, violent, transient. So this is, I think it is really a fascinating piece of the universe that you are discovering and understanding. And again, this, to me, this is already remarkably interesting. But this also, if you are interested, and we are all interested in fundamental physics, in understanding the fundamental laws of physics, these are also extraordinary laboratory. There are extreme conditions that are essentially impossible to achieve in Earth laboratories that you can obtain. So actually, this is, I'm going very quickly. The first glimpse that there was something interesting was the discovery of cosmic rays. The story was, I can go quickly, there was radioactivity, and then people look for radioactivity, but the radioactivity was seen as ionizing radiation. But ionizing radiation was everywhere. So of course, radioactive materials are everywhere, but people had the intuition. Actually, Charles Wilson proposed already in 1901 that there was too much ionization, that there had to be maybe something coming from outside. There was not enough radioactive material in the substances around us to create all these ionizations. But it took a decade to obtain this, and then this was obtained in 1912 when Hess and Kohl-Horster, actually the discovery of cosmic rays, it has been in 1912. I mean, a few years ago, we had the centenary. There was a lot of discussion. And so actually, just very quick, just a mention, but I wanted to say the early time of cosmic rays was very exciting because the understanding of this radiation came together with the birth of particle physics. You were detecting these secondary particles. And in order to understand the primary particles, you had to understand all the development of the shower. This is a very old Wilson chamber, and people were studying what was happening. It was an exciting time. And there is a beautiful story. We discovered the positron, understanding electromagnetic shower, the muon, the charged pion, atmospheric neutrino, nuclear interaction, strange particle. And I want to say that one important, crucially important point was made by Homi Bhabha, which actually I've been learning about this remarkable person. And as you know, this is a passage, a paper written in 1936. I think he was, 27, 28. Anyway, it was in his 20s. Actually, Walter Heitler was, I think, 31, 32, and they understood the development of the shower, which was remarkable. Heitler and Bethe understood the pair production, and then they put together pair production and Bremsstrahlung and understood showers, which was fundamental element of this. And I just wanted, and then of course there was a question of extensive showers, which were discovered very soon. And actually this was just extraordinary. At the time, in the 30s, there were no particle accelerators. So the particle, there was radioactivity. And here you had 10 to the 15, 10 to the 16 electron volts. Pierre Roger, because he was finding the showers, which was filling several hundred meters of space. And actually we know, and actually he predicted correctly on the basis of Daba theory that these were electromagnetic showers which had to have this sort of energy. And so somewhere in the universe, there were places which was accelerating particle at this extraordinary high energy. And actually, I just want to say, the question of understanding the development of the shower is still at the frontier of science, because actually, and I'm very glad to be able to go to Houthi in a few days. And when you study the showers in Houthi, you have to understand hadronic interactions and so on, and understand all of this. But let me go back to this. So actually, for a long time, there was very little progress in understanding where these particles were coming from, okay? And the reason is simply because you don't image the source. Particles are bent by magnetic field, and they go through very complicated trajectory. You don't see them. You see them all mixed up. And so the question remained open, and to some extent is still at least partially open. And this is because you were not seeing the sources. And now we are starting to understand this question, and we have the answer is very rich, as I hope to communicate to you. And so actually why, and the reason is that cosmic rays now come together with other messengers, which are photons and neutrinos, and we see also gravitational waves can have a role. And these four messengers clarify this question. And the thing is simply, cosmic ray, photons and neutrinos are inextricably tied. And this is actually very simple to explain. Let's say this is a medium, and you have these lines are relativistic charged particles, protons or electrons and positrons, and you see they are immersed in a turbulent magnetic field. They have complicated trajectories, so they are confined here. Some particle will leave and then make the cosmic ray you can observe at the Earth, but wherever there are particles there will be emissions of photons and neutrinos. And the reason is this. There are actually two mechanisms for the hadronic, the interactions of protons and nuclei. Protons and nuclei interact with some target and make pions. And the pions decay, so the pi zero, goes in a pair of photons, and the charged pion, so the pi plus goes into mu neutrino, and then there is a chain decay, the muon decay in positron and two neutrino. So for each charged pions, you have 3 neutrino, written here in blue, and for each pi zero, you have 2 photons. And so actually, wherever you have relativistic protons, nothing is really empty in the universe. So these protons will interact and emit photons and neutrinos, and these things can see, and so you can trace wherever relativistic protons are. Similarly, if you have relativistic electrons or positrons, this can, they can Compton scatter, and generate, actually, a relativistic electron can scatter with an optical photon or an electron volt photon and generate a photon of the same energy. And then you have Bremsstrahlung and synchronous radiation. And so you can trace also the presence of positrons and electrons via these processes. And actually, it's important to understand the role of relative acceleration of protons and nuclei and things. And so actually, this is the idea. This is like a source. This is actually the scheme of an active galactic nucleus. And so the source can emit cosmic rays, which are bent, and so they arrive with no directional information, but they can arrive from different objects. And then they can emit photons and neutrinos. The photons can be absorbed The neutrinos are much more difficult to see, but they have the advantage that they traverse and can always be observed. And so, well, what about gravitational waves? I'll try to say something later. But the point is that these accelerators are associated to, to the formation of compact objects. They're associated to events, to transient events, like supernova explosions, gamma ray bursts, jets of active galactic nuclei. So places where you accelerate large masses to very large acceleration. And large masses with large large acceleration is exactly what make big gravitational waves. And so you can, some of the sources of cosmic rays will also emit gravitational waves, and this is the connection. And so actually, let me just say, well, I can nearly, well, let me just represent this. This is something which now is solidly understood. The cosmic rays that from Hess to Auger were understanding, that Baba and Heitler were modeling, we are quite convinced of this. So this is the scheme of our own Milky Way. So this is the solar system. And here I've represented some kind of point-like sources, which actually are both point-like and very likely transient. And they generate cosmic rays. And the cosmic rays remain confined for a finite time in the Milky Way. This is our understanding. And they remain confined, and actually they form a bubble around. So this is again the same scheme. This is just to scale. This is our the large and small Magellanic Cloud, some satellite galaxies, and they make a bubble. Actually, we still understand only partially how this bubble is formed. Okay, but actually it's very important. And actually, you can study the property of the bubble with what's called the diffuse gamma ray flux, and also the neutrino diffuse flux. Because if I look in this direction, I will integrate all the emission. So the emission from this bubble is due to the product of the gas density in the galaxy and the density of cosmic rays. And actually, also we now understand that, of course, most of the cosmic rays are galactic, so they're generated in sources in the galaxy. But you have other sources that you have. This is kind of a piece of a galactic space. So this now is the Milky Way over here, and then this is just conceptual. Right? And then you have other objects, some of which could be like the Milky Way, but you could have different objects that can generate cosmic rays, and it's very, very likely that at a certain point the highest cosmic rays become extragalactic. And okay, so this is I think this is what I just have said. So now we have all this direction of study. One of the, but actually, maybe I should read this. But okay, no, I think I have. So now you can measure the cosmic rays, and now actually this one, I think this is still a field which is of high interest. And you want to measure as precisely as possible, sorry, the fluxes of cosmic rays as a function of energy and direction for different type of particles, protons and nuclei, electrons, but then of course also positrons, antiprotons, and so on. And actually, recently, but not recently, I think it from now it's already 15 years or so. From May 2011. There was this is is currently the best detector for measuring cosmic rays until around 1 TeV, which is the antimatter spectrometer on the International Space Station, and it has measured. Yeah, okay. So this is the proton divided by 100. We see these are the electrons, positrons, and antiprotons. There will be a lot of discussion of what we understand about these cosmic rays. But then, of course, you want to measure at higher energy. And so this is actually detectors for higher energy. And actually, you see that the spectrum has some features. This is the spectrum multiplied by a power of the energy, the power law, just to make more evident what the structures are. And you see that there are these features which now people try to measure accurately and try to understand. And so this is again a kind of a description. Sorry, this is my work on one. Actually, I took this picture I think in 2009. So probably the detector is different, but so the UTI activity is related to this precise measurement of the spectra. And I would like to just to remember, actually, I'm sure you will hear, or I've already heard, more detailed discussion. This is a beautiful physical review letters published last year showing the structure, which actually I think has been recently confirmed by the LASSO experiment. And so actually we are trying to measure accurately these spectral shapes and try to then interpret them. The interpretation is difficult, and I will not say this, but actually the problem is in some way is to construct the contribution of different sources to construct the spectral shape. Okay, so this is the idea. And of course, well, very interesting is the study of the highest energy cosmic rays. And so for this, you need something much larger than what UTI is. And this is the largest detector, which has obtained very interesting result, which is the Pierre Roger Observatory in Argentina, which is larger, 3,000 square kilometers. Actually, this is one of the elements. This is the equivalent to one of the little boxes of UTI. And each box now is separated by 1.5 kilometers. So this is kind of a triangular grid of 1.5 kilometers. And in fact, you don't see the other. So you see all these objects. All of these objects have their own power from solar power, and then communicate by radio. There are no cables because these are too far. And so this, and then there is what's called a fluorescence telescope. The shower during the night makes some light, and like this, the particle excite the molecules in the atmosphere, which radiate light, and you can reconstruct the development of the shower. And this has revealed, again, interesting structures that you have to understand to reconstruct the spectrum. And you can also measure the type of particles, because see, the area is really the energy of the particle, because this is how much ionization the particle created. And the shape depends on the mass of the nucleus. And the result has obtained actually some really interesting result, because they find that the composition at high energy has, well, you see, is something like this. This is from their work. So you have a combination of particles that enter a different energy, like proton, helium, carbon, oxygen, and this will be the higher mass. And this is a structure that nobody was expecting, and people are trying to understand. And here there is again a parenthesis, but I'm really interested into this. When you are at this high energy, the highest energy particles, which are the order of 10 to the 20 electron volt, correspond to a central mass energy 433 TeV, when the maximum energy that we have obtained is at LHC 13.7. And so you have to model hadronic interactions appropriately in order to model these showers. And this is a very interesting problem. And this is actually, it's again, that I think there is flow of information from accelerators to astroparticle physics, and also possibly from astroparticle physics to accelerators. Okay, I like to call QCD the dark side of the standard model, because it's something which you know the fundamental Lagrangian, but you're not really able to calculate, the spectra of pions and kaons and so on. The soft part of QCD you cannot obtain. And a word about anisotropies. So this is, if you analyze the spectrum of cosmic rays is nearly perfectly isotropic, but there are small deviation. And you see, this is 1 TeV. So this is 1 per mil. So this is perfectly isotropic at the level per 1 per mil. But people are capable of measuring this 1 per mil anisotropy. Okay. But if you go and then actually in all this range, you only have upper limit at the level of the 1%. And actually, when you go at the highest energy, you have 10% dipole moment. So there is in that direction, and in that direction, the spectrum is plus or minus 10% of the things. And so this is, you see, this is, well, okay, 6.5, sorry, I exaggerated a little bit. And actually, the question is, where does these things point? And it points in a direction which probably is related to the near structure in the universe. So what people, the Auger people, I've been discussing that this is a sign that these particles are high energy, are extragalactic, and map the local structure of the universe. Okay, so let me say now something about gamma rays. Well, gamma rays, you know, a high energy photon just travel a 30th of the atmosphere, then it's absorbed, make a pair. So in order to see them, you can either go in space, or you can, at very high energy, you can see the showers which are generated by these particles. And so you can make some ground array, or you have this Cherenkov, or various type of ground array of Cherenkov telescopes. Okay, so these are represented. You can either go in space, or you can make a ground array or a Cherenkov telescope. The Cherenkov telescope does not see, can go to lower energy, because the shower is absorbed, but the Cherenkov light arrives and can be imaged in these detectors. And so this is the Fermi telescope, which I think is in flight since 2008, I think, and has obtained a remarkable set. And this is an image of the Cherenkov telescope. I wanted to say the Cherenkov telescope has been a powerful, wonderful instrument which has obtained a wealth of remarkable things. This is magic, and this is Hess. I'll present a few results of Hess in Namibia. And actually, I'm really very glad to hear that India is participating in this game. And so this is, I think actually this has been inaugurated in the 4th of October. I'm not sure when this picture was taken, if it's how different it is from this. But I think the potential of this, and this is a very remarkable advantage, of course, that this is located at 4,300 meters of altitude, which has a lot of advantages. So actually, let me go. Now, this is the sky seen in gamma rays from Fermi at an energy of 100 MeV. And actually, you can clearly see, first of all, that there is like a diffuse flux. So this diffuse flux is what is mapping this bubble of cosmic ray in the Milky Way. And then actually, you can see several points. And actually, well, so this is again, this is called this diffusion mission. So you integrate in this direction, and integrating in this direction, you see the distribution of cosmic rays around the galaxy. So, but then the interesting thing is actually now the catalog of Fermi lists 7,195 sources. So now we know that there are many objects in the galaxy and in the universe that accelerate cosmic rays, because these photons are essentially generated by relativistic particles which are inside or near sources. And so actually when you say, we don't know which sources are those who generate the cosmic ray that we see here, but those are sources that accelerate cosmic rays, okay? And so actually, if I make, actually you can also see here by eye, and you can see that there is, you see, this is equal area projection. So you see that you have an isotropic component, which is which is flat in this representation of the 4 pi of the sky. And then there is an axis on the galactic plane, which is over here, which of course, most of the particles toward the galactic center. And in fact, actually, if I plot as a function of the sign of the galactic latitude, okay, you can see here, you have an isotropic distribution of extragalactic sources, and then sources concentrated, most of them just in a few 2-3 degrees around the galactic plane. And these are the sources in the galaxy. And actually, it's interesting. You see, the red things here, there are more than 4,000 objects. And these 4,000 objects are active galactic nuclei. And so this is actually one of the simple things to remember, that active galactic nuclei, please.
The red part should be flat all along.
The
red part
this line here, if you have an isotropic distribution, isotropic on the sphere, the distribution in the sign of the latitude is flat. Around here, yeah. Well, here this is it's go down here because you have to see a source. The source must be brighter than the background, and toward the galactic center you have more diffuse flux because there are more particles. And so this is an effect of of seeing a source over the diffuse flux of the cosmic ray population.
Not the actual thing, just because you are looking from the background. Just because you are not able to see them properly, or?
You have less sensitivity in this region. So this is why this red line is going down. You know, an AGN which is not here, you can see fainter AGN that's over the galactic center. The galactic center is a region. So this is an effect of efficiency in source detection. I hope I answered, but yeah. So again, this is I'm just going. So this is actually a table. Here I wanted to point to. These are extragalactic sources, and this is what I say. There are 4,006 sources identified as AGNs, and I will say something about more. Then actually there are 6 galaxies, external galaxies, which are seen, which actually is very interesting because it's like the Milky Way. They contain cosmic rays. These are starburst galaxy. These are Seyfert galaxy, just a few of them. And if I look at what sources are seen in the galaxy, you see there are many types of sources. Pulsars, these are millisecond pulsar, supernova remnant, pulsar wind nebula. This is a mixture of supernova remnant and pulsar wind nebula. This is globular cluster, star formation region, binary system, and nova. So you have many. There are different classes of objects that accelerate particles, and actually, would be having a few hours, you could go through all of this and try to discuss the properties of this object. Here, I want to give I'm kind of giving an impressionistic talk, but the message here that you have objects which you still, many of them you understand only partially, but that they're very, very interesting. And so this is actually, it's a similar thing. This is the TEV-cut, I mean the TV, well it's 1000 GeV, and so these are obtained mostly by Cherenkov telescopes. So this is not a full map of the sky, because these are pointing detectors, and so they look at different parts of the sky with different sensitivity. But again, you see, this is the same kind of projection. I think actually we are now. This was maybe now we are approaching 300 sources, because you are continuing to observe. But you have galactic sources and then extragalactic sources, and the extragalactic sources again are kind of isotropic, and then you have the sources toward in the disk, and actually this is the most precise collection. The detector in Namibia is the one who can see, which is in the southern hemisphere, can see the galactic region, the galactic center region, and as you see, seeing several objects, and actually 78 sources in these things. And again, you have supernova remnant, pulsar wind nebula, binary systems. And so you see these classes of objects, you want to understand them. So I just want to say a few words about them. Supernova explosions have been predicted for actually quite a long time as the main source of cosmic rays. So this is one example. This is Cas A, when actually he has a pulsar at the center, a neutron star. So this is the result of a gravitational collapse. And this is the expanding shell of the ejecta material. And the prediction was that, you see, again, the ejecta act like a piston who generate a shock wave propagating in space. And this, if you want, this fluid, this rapidly moving fluid, is what carries the electromagnetic field, which is capable of accelerating the particles. That's I'm not going to enter. So this is the kind of what's called second order Fermi acceleration, which actually now I'm not going into it. And actually there are I think there are several tenths of supernova remnants which have been observed, and it's clear that around this object there are large population of relativistic particles, and also there are protons and nuclei have been detected, and it's unclear if this is sufficient to generate most of the cosmic rays. But and actually, this is you're actually finding a picture which is far more complex than what you're expecting. So these are spectra of different objects, which you see have different forms. And so actually the question is, well, and they do not extend to very high energy. And so there's been a question of what does this all mean? And people are still trying to resolve this. But what is clearly established that these are capable of accelerating large quantity of cosmic rays. And the total energy in the relativistic particle around some of these objects is close to 10 to the 48, 10 to the 49 erg. So very, very large amount of energy. And another really fascinating class of objects are pulsars. And so you know what, this is actually the Crab Nebula, which is the remnant of the supernova which exploded in 1054, is across a large piece of the spectrum, the brightest object in the galaxy. And so, you know, he has the period of the crab is 0.303 second. And actually, you see the crab is slowly spinning down. And the spinning down, the energy which is extracted from the spinning is emitting in a wind. Actually, this is the famous first detection of pulsar by Jocelyn Bell in 1967, which is a beautiful story, but you probably have heard. So the spinning down of the pulsar emits a wind of particle, and this wind is probably what accelerates. And there are strong reasons, very convincing reason to believe that and actually this, now the Crab Nebula is measured with a broad spectrum, and this broad spectrum reaches more than 1 PeV, so which is 1,000 TeV or 1,000,000 GeV. And actually very likely all these particles are electrons and positrons. And you say this because you can match the synchrotron emission to the gamma ray emission. And so the general idea is that the wind, actually the electromagnetism of the pulsar, the fact that you have this object rotating so quickly, which is strongly magnetized, how this manages to create wind, it's a fascinating, really beautiful question. And so this wind of particle can accelerate this plasma of electron and positrons and generate this these events. And so actually the pulsar wind nebula is the nebula. So actually there is emission from the pulsar itself. But then there is this nebula, which is the particle just accelerated around the pulsar. And actually one thing that people are now understood, so this is actually a piece, this is a very famous pulsar called Geminga, which is the Gemini gamma ray source. But anyway, and that around several of these objects, there is what's called a TV halo, a volume. Okay. So let me say something about active galactic nuclei. Well, we know that there is that there are large supermassive black holes around all the galaxy. So this is the black hole around our own galaxy, which is well established. And you know that the black holes are actually the brightest objects in the universe because of accretion power. So there is a matter accreting on the black hole, and the gravitational wave, which is gained, can generate really very large luminosities. And okay, I think I'll jump these two things. Actually, I wanted to show, this is, I think this picture, you know, this is the famous first picture published in April 2019 of M87. I thought actually it was quite interesting how this picture became popular and known and seen everywhere. And this actually, well, you can see that this is well matched. You can see that the size of the black hole is equal to what is predicted by general relativity. Well, this is the innermost stable photon orbit. So this is really, you're imaging this black hole. The point I want to say that M87 is actually, it's an object which is profoundly fascinating. And you know that this is it's probably actually the first jet which has been observed in astronomy. It was observed already in 1918, because it's a jet that actually there is a jet only on one side with no counterjet. So Herbert Curtis, a curious straight ray apparently connected with the nucleus by a thin line of matter. And now there is an understanding. So actually, this is seen in different wavelengths. And actually, the jet is made of blobs, and these blobs moves across the sky, and you can trace the movement of these blobs. And actually, you see that there was a counter jet. So this jet arrived, and then they make big blobs of radio emission. And you know the remarkable things, and this is that these blobs move at what appears to be superluminal motion. So they move, knowing the distance of this object, the movement across the sky would imply a speed of 6c. But actually, you know that the explanation of this is that really you are looking at an object which is moving toward you. And so this means that actually that the gamma, the Lorentz factor of this jet, is of the order of 6. And actually, it's quite interesting that this black hole here is generating jets with a bulk motion of the order of a gamma of 6, and now the additional measurement of the what's called the Earth telescope are trying to study the magnetic field which is at the source of these jets. And this is actually one of the most fascinating, I think, fascinating pieces of this universe. So the message that I want to give, you see, these are measurements both of Fermi and of the Cherenkov telescope of this object. So M87, so the first image black hole, is kind of the prototype for an active galactic nucleus. And actually, the emission, as you say, these are measurements of Cherenkov telescope at different time, because this is very variable. And in fact, actually, these sources are so variable because they're marked by different events of accretion that generate this. And so actually, the concept is somehow there is accretion on the black hole, the jets are emitted, and these jets are capable to accelerate particles and generate these gamma ray sources. So I say, when you say active galactic nuclei, you have a big family of objects, a real zoo of different objects. And it's interesting that the 4,000 is nearly most of the source, but the large majority, but it could be 98% or something, of the AGN seen by Fermi are blazars, or which is, okay, will be a story of this. But so our object, maybe I think I've written here, yeah, most of these objects are believed to those where the theta view is 1 over the gamma jet. I mean, if you have a beam moving with a Lorentz factor of gamma, all the radiation is emitted in a cone of the order 1 over gamma. And so actually, these are really, in a certain sense, rare objects in the universe, but they are so bright for this reason. So okay, so this is the general scheme. You have the black hole at the center, an accretion disk, and a larger torus around the disk, and then there is emission. So the AGN seen by Fermi are those that are pointing in the direction of the viewer. And this is actually a topic. The galaxy contains objects which are micro version of the quasar, of quasars or blazars, and they're called microquasars. And those are binary systems with where one member is a black hole of stellar mass, of course, that accretes from a companion. Let me just and actually this has been in the last well, very recently in the last year there's been a lot of attention of this because of a series of really beautiful measurements, which I will just show you. But okay, this is an artist's view of a binary system. So here you have a black hole, which has, again, the same structure. So there is, and this is the companion. Well, of course, the companion which are very near are those who make this game. So there is accretion from the companion to the black hole. And this generates, again, this accretion power, an accretion disk, and the emission of jets. And you have a number of these objects in the galaxy. This is actually a spectacular one, which is called GRS 1915 plus 105. Actually, here you see the two jets. And they say these blobs, which are emitted in the jets. And actually, you see, here you have two lines, because one is toward you and the one is behind you. And so actually, you see that they have different velocity, relative velocity to the center, because of, actually you can reconstruct. So this blob move at beta equals 0.92. And actually you can reconstruct the whole geometry. And you see actually the one toward you is much brighter than the one behind you, just because of effect of the Lorentz effect. And there have been this is another object. This actually has been, in a sense, the first microquasar discovered. At the time, the word microquasar did not exist. And well, this again is an artist's view, but I wanted to show this has revealed something very fascinating, because these are measurements by Hess. I will show you here. So the binary system is here, and actually you see that the gamma ray from this object is made by the two parts. There are two blobs on the two sides. Yeah, actually Hess is written here, and this is actually from this paper here, which is the January of last year. And so this is the black hole, and these are the jets which are emitted. And the idea is that the jets interact with some clouds on the two sides. And then what you are seeing is that the interaction of these jets with this gas, which then are capable of accelerating particles. And actually, recently, in October, I don't know if this is already published, I think it has been submitted also to Science. There is this paper of the LASO collaboration. Again, actually, this is of several of the sources of black hole jet systems. And actually, there are several papers which have been said that galactic cosmic ray could be accelerated in object of this kind. And okay, so this is again, it's an image of the same. This is actually, it's a well-known, the supernova remnant. I think this is called the Manatee nebula, because it looks like the manatee it's a sea animal. But you see, actually, this is probably a supernova which has been distorted by the effect of these jets. And again, here, see, the jet propagates, it's kind of invisible for a while, and then it becomes bright when it emits. And so there's been a lot of attention about this and what it means and what the jets are made of and how they produce things. And okay, I find that the reason, here I've talked about the reason why black holes and make jets is a fascinating question. And so how you can extract, so this is an idea which is very attractive, and people are working in understanding this. I think this is, it seems to me that this is clearly a problem of central importance. And I think I'm miscalculating my time. So maybe I'll just say, because there are, I'll go really quickly. You know that there are gamma ray bursts. And gamma ray bursts, this is a family of these lines of these objects which are seen. And so this is actually from Fermi. You see an isotropic distribution because these are extragalactic objects. Okay, let me say, and with enormous energy. I think this, you know, this there are two types. If you make the time of the gamma ray burst, so this is called T90, the 90% of the fluence. You have you have clearly a bimodal distribution, and so you have a component, a short component, which has an average of 1 second duration. And I mean, it's with a broad distribution, some very short, but you see this is 2 log normal distribution and a long component, which 30 seconds of average time. And it's interesting that these two objects, if you look at the distribution of redshift, actually you see that the long GRB come from very, very far. So this is 9, 10 redshift. And the short GRB are much closer and intrinsically fainter. So it appeared clearly long ago that these were different phenomena. And actually the long GRB, now they are clearly associated to supernova explosions. This was the first time. This is the first time a GRB was imaged and it was matched to a galaxy. And so actually you can also measure the redshift from the galaxy. And again, actually, you see, these are long from gamma ray bursts where you've seen the galaxy, and you always see supernova explosions. While for the short ones, you do not. And okay, and so actually, this is the theory that the long duration gamma ray bursts are essentially phenomena that happen probably during a certain type of supernova, while the short gamma ray bursts are coming from merging of neutron stars. And here I had one example. See, this is one of the first objects in which which was understood as a kilonova, which is the effect of the nuclear effect of a neutron star background. And okay, so I think I'll jump this discussion. So one of the things is that, but actually I wanted to, you know, this is one example. This in 2014. Now this has been overtaken. That the gamma ray burst is what you are seeing is very likely you are seeing those events in where the jet is pointing toward you. And okay, and they have enormously rapid enormously large Lorentz factor. So can I apologize. If you want to leave, I'm not offended. It's my fault that I'm. So don't stay if you. So, but I wanted to. Sorry, I apologize. I miscalculated. So I wanted to say something about neutrinos, and the information is complementary to gamma rays, the interesting things that they can observe hidden sources where the gamma ray are absorbed inside the source, and it can also observe galactic sources at high energy when the photons are absorbed. And so actually, let me make it just a more general comment. In all of this field, the ingenuity of constructing the instruments to see this, it's very, very interesting. And this is perhaps the most fascinating one, how you have built this telescope capable of observing this neutrino. And so this is the concept is that you need very large volume which are instrumented. And so the idea is that you instrument essentially kilometer cube of transparent Cherenkov medium, and you where you have inserted a photo detector. Actually, I understand that there is a participation, an Indian participation in IceCube. At least Ramiz and I don't know what other colleagues are participating. And this is a detector which has obtained really fascinating results. So this is actually really, it's the South Pole. So and you see you make holes in the ice of the South Pole, and you see these events. And okay, and again, I'm just so what I want to present three results of IceCube. The first one is IceCube has found evidence for an astrophysical neutrino signal, which is isotropically coming from the ensemble of the neutrino sources. And okay, so this is seen both from events where the neutrino interacts in the detector. This is called high energy starting events. They start because, so actually you have a time. So you have a neutrino that enters, you leave things getting out of the detector, but because these are early times. And so you can measure these neutrino which are interacting. So this is a new E event. This is a new mu event, okay, and then you can see upgoing muons, and you obtain this. Okay, let me just show this. So you see, so this is actually the prediction of the atmospheric neutrino flux, and above the result of the atmospheric neutrino flux, you see this isotropic astrophysical neutrino results, and probably the difference between these two things is only is within systematic errors. There's been a lot of discussion, okay, maybe I just wanted to talk briefly about the two largest events in the neutrino sky. So you have this isotropic diffuse flux, and the two brightest sources in the neutrino sky are these two. One is a blazar, which it was announced in July 2018. Actually, this paper has more than 1,000 citations, has generated a lot of discussion. And actually, the second source, which has been announced as a possible source, is a Seyfert-2 galaxy. It's called NGC 1068. Actually, this is Messier 77. This has been announced in November of 22. I think there are more than 400 citations now. So there is a lot of theoretical interest in discussing these objects. And so actually, this is the publication which announced the discovery of this. And actually, this was the story is actually quite fascinating, because IceCube saw this event. So this is a muon that traverses a detector. And this muon, is nearly horizontal. It's 5 degrees between the horizon, and actually, it's interesting. You see, what you see. I just wanted to illustrate the concept. You see that there is energy deposited in the detector, and so the energy deposited in the detector is 23 TeV. But then actually this means that the muon had a typical reconstructed energy of 52 TeV in the detector, entering the detector. And so actually what is the neutrino energy? Well, you don't know. You have a whole distribution, which is estimated to be of 290 TeV. So you have visible energy, muon energy in the detector, muon energy at birth, parent neutrino energy. So this is this event. And actually this event was given, was announced as an alert and say, people, look in this direction. And people did. And people found magic and Fermi that there was an AGN which was flaring. Okay, so this is the event of ice cube. And here is the AGN. And these are the map of Fermi and of magic. So when there was this event, there was a flaring, and actually there is possibly another event measured by the Baikal detector. And if you're looking at archival data, there is evidence for additional emissions, and especially during a period between September and March in 2014. So actually, this is an image, a radio image of this object. This is an object Z for 0.33, and okay, so this is again, it's a superluminal motion with beta apparent 3.7. So one thing which obtain a lot of discussion is why TXS and not others, so TXS is one of it's around, as I say, there are 4,000 blazars by Fermi, and this is like number 50. So it's bright, but not one of the brightest. And so the question, why not the other ones? And there have been a number of studies, and it seems that there is not a good correlation between the blazars of Fermi and the the neutrino observations. And actually, this is the second source, which is very interesting, is NGC 1068, and this is the signal. Actually, see, this is the region of the detection, and you see this circle here. This corresponds at the galaxy, and so this is the galaxy which we're seeing well inside the position where you have the excess of events, and okay, so this is the same thing. This is his position in the sky, but this is the interesting part. The interesting part that this is the signal of ice cube of these neutrinos, and these are the measurement of Fermi, and these are upper limit by magic, and so actually you see that. The ice cube result is significantly larger than the upper limit on photons. So this means that somehow these neutrinos are not accompanied by photons. And the explanation, as I said, there has been a lot of discussion. So this is actually the overall spectrum from radio to the highest energy. And so the explanation for this is that, you see, actually, this is the point. Cipher-2 galaxy are you see, blazars are the one more toward to the jet, and Cipher-2 are the ones which are closer to the opposite, 90 degrees position. And so actually that the photons are absorbed. And so the emission is not from the jet, but is from very near the black hole. So this is, so actually this is just, the black hole at the center of Messier 77 is 6 million, 7 million solar masses. And you see actually that this is kind of the luminosity, this is the total luminosity of the AGN. And so the point is that the gamma emission is much smaller because it is absorbed, and the speculation, which is now fairly commonly accepted, is that most of the extragalactic signals seen by IceCube is due to not to the jets seen by Fermilab, but most of it is coming from emission from a region much closer to the black hole. Okay, so I wanted to say something, but this is the cover of Nature last week. And I know if you have seen it, this was announced the 13th of February. And there is the observation of a ultra energy event. And I just wanted to say that this again has obtained a lot of attention in this week. And there are several papers who appeared with explanation. So this is KM3net, which is actually under construction. At the time, this is actually the same concept, but under the sea. So actually, I found it's amusing to show how they deploy. So you make the strings. So actually, these are all this string with this optical modules. And so they put it like this, and then they unroll it, and the things. So there are all these detectors with 36 meters separation, and this is an event of extraordinarily high energy, which is 10 times larger than what has ever seen by IceCube, so the neutrino energy is 220 eV, which and this has well. The meaning of this event is generating a lot of speculations, and people don't know what it is and what it comes, and it could come from cosmogenic neutrinos. Okay, so I feel that I really exhausted my time. I wanted I just mentioned the title. So it's about gravitational waves. I think I should give, or actually, I think gravitational waves, the potential for gravitational waves in the future, I think is of extraordinary interest. And I'm really glad that India is planning to participate into this with LIGO India. And I think you have known about all these results. I think that this is the example that is really remarkable. So there is one of this merging or observing by. So here I had a list of the. There is a catalog of the merging seen in gravitational waves, and just one of them is consistent with the merging of neutron stars, neutron star, and there is this remarkable thing that this event, with a delay of 1.7 seconds from the time where, if you want, the frequency of the signal diverges, after 1.7 seconds, a GRB, a short GRB, appears in the sky. So this is actually a clear examples where you have the merging of an object, emission of gravitational waves, and then a gamma ray burst, which with emission of visible photons. And this is really very exciting. I think there is one paper actually by Luca Rezzolla, and say this is the most beautiful laboratory, more beautiful experiment ever seen. So you have two neutron stars which merge. So this is actually a simulation of what happened when the neutron star merge, and actually you have a hint that the jet is starting to form. And so here you have extreme gravity, black hole formation, emission of gravitational waves, complex microphysics because they're the matter of these neutron stars that merge, and electromagnetic processes which are particle accelerator. and then ejected material, nucleosynthesis. You have all of this together that you want to study and understand, and you have ways to do it. So I think this is really, in some sense, this is a very lucky event that you have this possibility of having this event, but it's really fascinating and shows how much you could learn in the future. Okay, so just to say, this is for the future. This is a network of gravitational waves. The two LIGO, Virgo, we participate in a detector in Germany at Max Planck instrument, Japan, and actually this is LIGO India. I think it's my best wishes for whoever is involved in this project. I think it's very valuable. I had one chapter of dark matter with that jump, because actually I would say, but I think actually I just wanted to say it's obvious that dark matter is a problem of such a great importance that each field should study dark matter. And there is a possibility, you always, I think you have to look for dark matter everywhere. And there are several ways in which you can look for dark matter in the high energy universe. In particular, just to say, dark matter could generate signal from different objects which are not seen, and you always have to do this, to study this possibility. And okay, so I think as I say, this is a field which I hope in this landscape I've shown you how many new things, how many new surprises there are, and there is a large program of experimental study to develop these directions, and I try to outline some of the motivation to study this research. I apologize for having gone so long. So anyway, if anybody wants to discuss, I'll be delighted to discuss more. Please ask Professor Mohanty, or currently I'm in room C121. Thank you for your attention.
Yeah, thanks for a very nice talk covering, such a broad spectrum of things in the astroparticle and, multi-messenger study. So now the floor is open for questions. Questions?
So KMC net staff, what is the status, or when they can have this complete?
Sorry?
KMC net.
KM3 net, yeah.
When they can complete their setup, both the.
Actually, I should know, but I think it's unclear. I don't think it's not only a technical problem, but also a funding problem. So they have a goal which they have presented, but I'm not sure. I cannot give you a good answer. I apologize.
Okay, sorry, I also know the funding issues.
The funding has not been. I hope that the funding has not been entirely. The funding has been a limitation in the project. Yeah.
Okay, are there any other questions? Yeah.
Any comments on these two purported events at ISRO?
Last week, to which follow-ups in gamma and X-rays have not been seen yet.
Which event? Sorry.
Purportedly, there are two events from IceCube which came in last week, very high energy events, which were around the time that the LVK, the LIGO, Virgo, Kagra gave a gravitational wave signal, but then we haven't seen a gamma or X-ray signal till now.
Yeah, sorry, I cannot comment on this. No, yeah, I'm not. Yeah. So
he is referring. There are some recent events which happened very recently. Which
There was a claim to be a binary neutron star event by the LIGO Kagra collaboration, which has been followed up in the similar time by the IceCube collaboration, and two events has been pointed out. not a confirm association, but in time they more or less similar. But there's nothing being seen in any other bands except in the radio for FRB. But it's very quiet in any other bands. So we don't know what is it so far. It's good to know. It's not late enough to be thrown away. Yeah.
So I was just wondering, is KM3net going to explore a different kinematic phase space, or is it just complementary to IceCube in the sense of direction? It will look at different direction. I'm just wondering, like, is it going to be something extra? It is going to compared to IceCube, or it is just
sorry, I heard only partially. The question.
So what I mean is, there is, to me, I mean, as a non-expert person here, to me, both IceCube and KM3net, the concept is the same. It's just one is ice and another one is water. I'm just wondering, is it going to be KM3net? Is it going to probe something additional in the sense of higher energy region?
I think the important thing is that they're complementary, because they see different parts of the sky, because one is as the South Pole and the other one is the Northern Hemisphere. So this has always been very much desired, that a telescope on the Earth as a partial view. So this I think is the most important thing.
It's the direction.
Yeah.
Okay, I see. Okay,
And
thanks.
yeah, actually, it's curious, because now both IceCube has demonstrated that it can see events both from the Northern Hemisphere, so neutrinos that traverse the Earth, and also events which are coming from the southern. So it has been, they're kind of trying to expand, but there are different, you see things differently. So this is actually, in some sense, in zero approximation, KM3net and IceCube, I think they're very similar conceptually. There's been a lot of discussion about the relative merits of ice and water. So this is it's a technical issue. There are advantages for both. I mean, I think a KM3net people would say water is much better, but I think it's not so obvious, because again, ice has a very the absorption length is shorter. It's longer. But water has better angular resolution. So there is a long discussion about the technical merits of the two. But the detector, I mean, the kind of spacing of IceCube and KM3net are similar. Then of course there are developed IceCube. IceCube has his own project of Gen 2 and so on. Yeah. Because of course the way you construct the geometry of the detector, you are more sensitive to different energy ranges.
Infinite can observe more higher energy than our IceCube.
Sorry?
Infinite can observe neutrino of more higher energy range than IceCube.
No. I don't think this is true. They have been very lucky in obtaining this very high energy. I don't think the sensitivity
PeV range.
Yeah, they just I think yeah. Incidentally, there are is talking about this, but there is if dedicating a few minutes to for the very, very high energy, and this is actually now becoming clearly different techniques are pursued. So there is a whole question of the radio neutrino telescopes, which then will have very much higher sensitivity at the very high energy. Yeah, and I think actually that is a very important type of telescopes to develop. So because you want to, yeah.
Hi. Yeah, it's a quick follow-up on this. That possibly you know that the US is kind of throwing away any mission beyond 2030 in on South Pole. And Ice Cube Jane 2 has got a hit on that from that as well. So is there any proposal to build Ice Cube Jane 2 like detector undersea? Because you said the concepts are similar. So.
I am not. I don't think KM3net has presented an expansion at high energy.
Okay.
They have already their hands full in constructing the detector. But let me say that this idea of going to high energy with this Cherenkov concept is under study by. There are at least two projects. One is Chinese. Actually, I apologize, but I don't remember the names of either of these two projects. But the Chinese.
Why will they build it?
But then there is also an American project. So actually, which wants to build something in the Pacific. So there are groups, there are ambitious groups which are thinking of. In some sense, probably Ice Cube, I think, is in pole position because as its techniques, but there are. I think it's healthy to have.
Sure.
But I'm not sure. I think we will hear the China actually a Chinese project which is very ambitious, and actually Elisa Resconi is a principal investigator of an American project in the Pacific. I don't have. Yeah. Okay.
Maybe,
sorry.
Okay. Thank you. Yeah.
Okay. I apologize
So,
for being so long.
let's
Thank you.
thank Professor Lipari once again for the wonderful talk. And yeah, please, join for that.